Hey guys, welcome back to my channel. This is the fourth video in the mathematical modeling video series. And in the past videos, we spoke about the population growth models and some basic models like that. If you haven't seen the previous videos, I'll leave a link right here and in the description box below, because some of those concepts might help you understand what we cover in today's video better. So today we're actually going to be starting out with the first disease dynamics model. And disease dynamics is one of the most important, and it's the place in which most mathematical models are used in today's world. So let's get started. So to understand disease dynamics models, we first need to understand what interacting populations actually mean. So in the previous video, I spoke about something called compartments. So to give you a rough idea, let's think about a country which has two states, right? State 1 and state 2. Now, this is a country. And there are only two states, state 1 and state 2. So there are some jobs which are there in state 1. There are some jobs which are there in state 2. Now, people tend to move or shift or migrate for jobs, right? Like that's usually why we leave our hometown and go to another place or stuff like that. So let's assume that there are people entering state 1 and there are people exiting state 1 as well, right? And there are again people entering state 2 and there are people exiting state 2 as well. So now state 1 and state 2 can be thought of as two populations within the whole population of the country, right? The sum of the populations of state 1 and state 2 form the total population of the country. So now if we are talking about two separate populations of state 1 and state 2, then we're actually talking about how those two populations are interacting with each other. What I just said is that some people leave state 1 and they go to state 2 for a job. Some people leave state 2 and come to state 1 for a job. Now the rate at which this happens can be different. It may so happen that in some years the number of jobs in state 2 are higher. So there might be more people coming. Or it may so happen that there are more number of jobs in state 1 in some particular year, and therefore more people end up going to state 1 and stuff like that. And of course, for people entering, there are also people leaving. So there's a balance, and this is how we deal with interacting populations. Now, this is just a very simple idea, and it's important for you to understand that if we are thinking of our country as, the boundary, like there are many countries in the world, but what we are discussing in this example is just defined and is just enclosed to the country. We don't necessarily care about other countries and other factors. Like for us, we're concerned with just the population of the country. That's it. And we're talking about the interaction of the population within that country, right? So why I explain this will be clear in just a minute. So one of the most popular disease dynamics models is the SI model, right? It's the SI model. So the SI model actually consists of two things, S and I. So I'm just going to tell you what these are called, and then I'll explain a bit about disease dynamics and why we need mathematical models for them and all of that. And I'll be using these two terms, which is why I'm just giving you an idea first. So S is called susceptible population and I is called infected population. Now, when we talk about a disease, right, there are some diseases which everybody can get. Like, for example, the current pandemic, right, COVID. Anybody is prone to getting COVID, right? Anybody can get it. It's not, that only male population can be infected by it, or only female population can be infected by it, or only the elderly. It's nothing like that. Everybody can get COVID. So the susceptible population in any disease dynamics model essentially refers to that population of people which is prone to getting the disease, which is susceptible to the disease, right? It doesn't mean they're infected with the disease. It just means they are people who can get infected by the disease, right? An infected population, very obviously, means it refers to those people, that part of the population which has actually been infected with a disease. So with COVID, for example, when somebody gets a test done and the test comes positive, so they become an infected person. So they get added to the infected population. Now, in diseases, if you think about it, there is always an interaction between an infected person and a susceptible person. So a susceptible person is just somebody who can get that disease, but he has not gotten that disease yet. Then there are infected people who have the disease, right? Some diseases which are transferred from humans to humans, again, like COVID, the infected population actually influences the susceptible population, in that if the infected population is higher, more susceptible people can get infected. Now, if you see what I just spoke about, we can actually consider two compartments, right? One is the S compartment and one is the I compartment. So S actually denotes the population of susceptible people, and I denotes the population of infected people. Now these are two interacting populations, right? And let's say I'm talking about only one particular country. Let's say I'm defining my boundary. So let's say I'm talking only about India. So in India, there are S number of susceptible people, there are I number of infected people, and with time this is varying. So it's S is not a constant, I is not a constant. They are both time varying quantities, right? So to be more specific, it's actually S of t and I of t, correct? Now, because the infection exists and there are infected people, some susceptible people will get converted to infected people, right? Why is that? Because I was susceptible, I somehow came in contact with an infected person, he transmitted that disease to me. Now I, who was susceptible before, now even I have become infected. Now, this is just the rough idea of the SI model, okay? So in disease dynamics or in any disease, there are so many factors to keep in mind, right? So to think about it, we need to think about, oh, is there a cure? Because if there is a cure, then some of the infected people will get, saved. They might get saved, right? They won't be infected forever. After some time, they'll stop being infected. So one question is there a cure? The second question is the cure a permanent cure or a temporary cure? So for how long will someone who's cured stay cured? That's another question. The third question is, do vaccinations exist for that disease? If so, how long will that vaccine give a person immunity? Then there's a question of, okay, what is the death rate of the disease? How many people die from the disease? Is it a very high value or is it so low that we can, kind of neglect it? These are all questions that come up when you're trying to model when you're mathematically modeling a disease, right? So the SI model is the most basic model which was ever made in disease dynamics, and it has some inherent assumptions to it. And like I mentioned, it's dealing with the interaction between the two populations of the susceptible and the infected. So now we first talk about the SI model without recovery. So we are assuming that no cure exists for the disease and no infected person can get, saved or anything. He will stay infected. Like, that is just an assumption we are making. And we will obviously fix this assumption very fast. So in fact, I think I will add a term here, without permanent recovery. Cool? Because later on in this video, we'll also talk about temporary recovery. So for now, these are the assumptions of this SI model. So we assume that the population size is fixed. So what I mean by that is, so whatever area is in question, let's say this is the area which is in question, right? So there'll be some susceptible population in this area. There'll be some infected population within this area. And both of them are time varying, right? Both of them are time varying. So what we are saying here is that the sum of the susceptible population and the infected population is a constant value. What that means, if you think about it, is that if any person leaves the S compartment, they necessarily have to enter the I compartment. And if anybody leaves the I compartment, they necessarily have to enter the S compartment. That's what we are basically saying. That's what this model says, that whatever proportion of people are leaving S, they have to enter I. Whatever proportion of I are leaving, they'll enter S. Why? Because the sum of the people does not vary with time. The sum of the entire population value, right? So at t is equal to 0, also the population size will be n. At t is equal to whatever, some capital T, also the population size will be n. This is not a time varying quantity. That is the first assumption. Now the second assumption is that n is so large that n minus 1 and n are almost the same. That basically means to say n minus 1 is approximately equal to n. Now the third assumption that we are going to make here is that individuals are born into the population with no inherent immunity to the disease. So if, let's say, there are some diseases, where you're born and you already have immunity from that disease, then you cannot use this specific SI model, which we'll be discussing today, for that disease. Now the next thing is, this is not an assumption, it's more of a terminology. So beta, this is beta. Beta is termed as the transmission rate, or the rate of transfer of the disease between people. Okay. So what I mean to say is, now for COVID, for example, once the disease dies down and we have all the numbers from all the countries all over the world that was, affected by it, and the biologists study it more and more, and also the computational biologists study it, they will come up with a value which gives you or tells you that how fast how fast the disease transfers from one person to another. And that is essentially beta. So basically if there is one infected person, what proportion of the susceptible people can that infected person convert from susceptible to infected? So what is the rate of transmission? So how fast and in what way is the disease transmitted? So that is beta. So just a quick note, beta is actually a clinically derived value. It's not a mathematically derived value. That's why I said people will study and understand the disease better and come up with a value. So most common diseases, like let's say swine flu, bird flu, all of those things, like common flu as well, there is already a clinically derived transmission rate available that you can actually find out. If you read papers that have been made regarding them, you can actually find out the transmission rate and use for the purpose of your mathematical modeling. Now the last assumption, and this is to do with the fact that we're dealing with no recovery and there's no cure or anything, is that once infected, the individual stays infected. So even with COVID, for example, right now, some people are recovering, right? But we have no clue whether that's a permanent recovery or they can actually get infected again, right? So that's not what we're talking about here. Here we're saying nobody can even get recovered. Once they're infected, they will stay infected. Now you might think, what sort of a disease is this and why does this make sense to model it this way? Now the thing is, like I said, these are the assumptions we are making when we start a mathematical model. So very clearly, the fact that nobody can recover is a slightly bad assumption, which we will slowly fix. But the point is that we have to start with the simplest thing and build on that. So we're starting with the simplest thing, which has the most number of assumptions. So now let's quickly look at what the mathematical model for the SI disease dynamics model actually is, right? So these are the assumptions, and now we'll look at the actual model. So the actual model consists of two equations. This is equation 1 and this is equation 2. Now the thing is, if you see, the rate of change of susceptible population is equal to minus beta S into I divided by N. And di by, so we'll just look at these two things for now. So what it says is the rate of change of susceptible population is directly proportional to this. So what is this? You might ask, what is S into I divided by N? So if you think about it, I'm going to write this term as S into I by N. So I divided by N. So I divided by N is actually the proportion of the population that is infected. Now, very logically, in any disease, which can be transferred, between people, if the proportion of infected people is high, there will be more susceptible people. Correct? And if the proportion of infected people is low, there will be fewer susceptible people. In the sense that, what I mean to say is that there are S susceptible people. Now, and there are I divided by N proportion of infected people. So S into I divided by N roughly gives you how high or how low the susceptible population can be at an instant of time. So, for example, let's say when the COVID pandemic started, let's say India had closed all borders before even one case was detected in India, like no international travel, everything was closed. Nobody could enter the country, nobody could leave the country. Then, even though the whole country is susceptible to coronavirus, it is, right? Because it's a disease that anybody can get. It's true that S is pretty much everybody in the country. It's true. But there are no infected people in the country, right? So the growth of the susceptible population, the rate of change of the susceptible population would be zero, right? So what I mean to say is, if by some chance their I is equal to zero, then ds by dt would in fact be zero, which means the susceptible population would just be constant. Correct? Now, why this is important, right? It's important to understand this beta si by n term. So I've explained what S into I divided by n roughly, denotes, and that's the logical way to think about it. So what is beta? Beta, like we already said, is the transmission rate. So I divided by n proportion of the population are infected. That's correct. But how fast or at what rate do they convert, or basically at what rate do they convert the susceptible people to infected? That rate is beta, and that is the proportionality constant in this equation. Now you can see that there is a minus term. So what does this minus term mean? So in any mathematical model which is represented by ordinary differential equations, these are ordinary differential equations. If there is a minus term, you can think of it in your head as basically there is the S compartment and there is the I compartment, right? So minus essentially means that something is leaving the compartment. Plus would mean something is entering the compartment. That's the way to visualize it. So if you see here, minus beta Si by n. So those are the number of people which are leaving the susceptible population. So where are they going? We made the assumption that the population is fixed. So obviously they have to enter the I population, and therefore it's plus because it's entering the population, because it's increasing the population size. So that should be plus. If something is decreasing the population size, it should be minus. Now, clearly these two equations, if you add them up, okay, if I add ds by dt plus di by dt, what do I get? I get 0. And so maybe I should write this a bit more clearly because this is very important. So ds by dt plus di by dt, which is equal to nothing but d by dt of s plus I, right? Because that's essentially the additive rule of differentiation. That is equal to dn by dt. n N is the total population, like I mentioned in the previous slide. And this is actually equal to minus beta Si by n plus beta Si by n. That's equal to 0. So we've seen that dn by dt, that means the rate of change of population is 0. What does that mean? That means the population is constant. This means that population is constant, which is essentially the assumption we made. So we now verified that the assumption that we made in making this model is satisfied. That means this model is correct given those assumptions. That's one important thing to notice. Now the second important thing to notice is you can actually transform this equation from beta si by n into this. And this is nothing but the logistic growth model. So that's just a subtlety of how it's modeled. Now, this is already a pre-existing model, right? It's not like we made, you or I, we didn't make this model, like this model existed. And this model is for a disease dynamics model where there is no recovery. That means if someone is infected, they'll stay infected, right? It could be so that we are just talking about, let's say, a 30-day duration, and the disease is such that in 30 days, nobody gets recovered. So that's why we are using an SI model, right? In 30 days, either you can be susceptible or infected. That you can't get recovered, nothing, none of that stuff exists. So it's important to understand how the model works and what is the essence of the model, because that way you'll be able to implement it for different diseases or even other applications, which I'll talk about soon. Now, breaking down the model, we already did that. We essentially spoke about, how the population is constant, which was our assumption, and stuff like that. So now let's say this is T and this is just population, not population. This is just number. This is just some numerical number, right? This is which denotes the population. Now, if we talk about the susceptible population, let's say S of 0 and I of 0 denote the initial susceptible population and infected population. Like I said, if initially itself there are no infected people, I of 0 is 0, then there's not much to discuss about, right? Because you can easily control the disease and all of that is where you just essentially have to make sure nobody enters into your system, basically that. So both of these are non-zero. Essentially, that's what I'm trying to say. Cool. Now, if I have S of 0, let's say S of 0 is, this is S of 0 and this is I of 0. Now S of 0, because ds by dt is equal to minus beta si by n. That means because it's negative, it's a decreasing rate. That means the population is decreasing. So initially it was S0, but as time goes by, it's decreasing. And di by dt is equal to beta si by n. Initially it was like this, but as time goes, it is increasing. Now, if you see I of 0 plus S of 0, or maybe I should write it the other way around. So I of 0 plus S of 0, which is basically the initial population, that's n, right? Now, because our population is constant at any instant, for all time instances, as we go, from the start of the origin, from 0, at any point of time, if I take, let's say I'm drawing this line, and let's say I'm drawing this line. So let's say this is T1 and this is T2. So at this point, the value is I of T1, and at this point, the value is S of T1. At this point, the value is I of T2, and at this point, the value is S of T2. So what this essentially means is that S of T1 plus I of T1 is also N, and S of T2 plus I of T2 is also N. It has to be because the population is constant. And we know that I follows logistic growth model, which is why it's the S-shaped curve. S also follows. S is like basically the negative of that. So it'll also be something like this basically. So yeah, so it'll look something like this. Basically, that's how the curve will look. Now, this is just a rough understanding of the basic SI model without recoveries, like assuming that no cure exists, nobody can recover. If someone is infected, they'll be infected. Now, we will incorporate the effect of recoveries. So I'm just going to do this. I'm just going to write ds by dt is equal to minus beta Si by n. Now di by dt is equal to plus beta Si by n. And I'm going to draw the two compartments also. So let's say this is the S compartment. This is the I compartment. And from here to here, beta Si by n went, right? This is negative and here positive. Now let's say an infected individual gets recovered, right? So if he gets recovered and let's say recoveries are not permanent, and I'll tell you what I mean by that. What I mean by that is if an infected person recovers, he is again susceptible. He is not like permanently recovered or anything like that. He is again back to the susceptible toll, which means for now he is not infected. He may contract that disease again. Like example for this is common cold. We get common cold, then we recover from it. But that doesn't mean we'll never get common cold again, right? But if you think about it for chicken pox, it's become in such a way now that once you get chicken pox, it's very, very, very unlikely that you'll get it again. So if we are talking about chicken pox, we can't use this assumption because their recoveries are permanent pretty much, right? Once you recover from that disease, you'll never get it again. So you don't go back to susceptible over there. You are in some other category, which we have not discussed yet. But if, let's say it's common cold, we're discussing common cold, the modeling of common cold. You recovered, you are infected, now you recovered. You again go back to susceptible. You may get common cold again in the same year, maybe in the next year also. It's possible, right? It's not like you have permanent immunity from it or anything. So that means something has to exit I. So with some negative rate, and that same thing will come and enter S with the positive rate. So what is that term? How do we model that term? So if you think about it, we're talking about basically the rate at which an infected person becomes recovered. So let like gamma be the rate of recovery. Let's say I am giving this term gamma, and gamma is a rate similar to beta. Like beta is the transmission rate. It's the rate at which people become infected, or basically an infected person transmits the disease. Now gamma is the rate at which an infected person becomes recovered. So that means gamma into I is nothing but the number of infected people who become susceptible. So that means gamma into I people will stop being infected and they will get added back to the susceptible population. So this is in fact the same term here, and the same thing will go and get added here. That's what we're talking about. Now again, if you add ds by dt and di by dt, the sum is 0, which again our population is constant. That was our assumption. So here in a very simple manner, we incorporated that effect of, okay, if someone can get recovered, not permanent recovery, but just recovery. So even in COVID right now, there is no proof that if someone is recovered, they're permanently recovered. In fact, there have been people who got infected again. So this might be a decent first level understanding of COVID, right? We can use this model for that, because if someone gets recovered, again, they get back to the susceptible population. Again, he or she is prone to getting the disease. But at that instant of time, they have recovered and they are not infected. So they are in the susceptible pool, not the infected pool. Cool. So Now we saw how to incorporate recoveries into the whole thing. Now, there are many more such improvements we can make. So you can ask, okay, like bird, chicken pox, for example. If the recovery is permanent, how do I model it? What do I do? And that is exactly what we're going to pick up from the next video. So this video essentially covered SI models in detail, including the assumptions, SI model without any recovery, SI model with recovery. And here, in fact, we discussed how we can add our own term, right? So you may have some other ideas in mind that you want to add. Maybe vaccination. How do I incorporate vaccination? We will obviously deal with that later. It's a slightly more advanced thing. So we will do that in the lectures to come. But that's pretty much for today's video. I hope you enjoyed the content, and make sure you like if you know enjoyed it, and subscribe to my channel, and let me know in the comments if there's anything specific you'd like me to cover, or if there was something you've always wanted to learn about mathematical modeling, and I'll make sure I do a small bit on that as well. So as always, thank you for watching, and I'll see you next time.